Morning.
Waalaikumsalam. Good morning, doctor.
Morning, doctor.
Okay. Right. So I just want to remind you regarding our test one tomorrow. So as what you can view from the Google Classroom entry, okay, the test will be held tomorrow, starting at 9:25. Yeah. So 9:25, we're going to start the test, but you'll be given 5 minutes to download the questions from the Google Classroom. Okay, so we are going to use the classroom for the medium, yeah, for the medium, right? So 5 minutes to download the questions, and then we're going to start at 9:30 sharp, and we're going to finish it by 10:30 a.m. Yeah. Right, and upon finish the test by 10:30, you'll be given another 15 minutes up to 10:45 to upload your scan answers. Okay, so you have to scan your answers, and please upload the answers in the Google Classroom. Okay, so I will not accept any submission through WhatsApp, yeah? So only a submission through the Google Classroom entries. Right, about the test tomorrow, there should be 4 questions. Okay, 4 questions. The first 2 questions will be asking about theoretical issues, theoretical parts that we have learned in class for chapter 2 and chapter 3. Yeah, chapter 3. And then for the rest 2 questions, 3 and 4, that questions will be dedicated for towards the calculation. Yeah, calculation. So overall, there should be 4 questions. All right. Is there any questions for test tomorrow? Okay, the mark for test 1 is 15%, yeah, as what we have agreed in our course information last time. Any questions for test 1?
No, doctor.
Okay, hopefully it's clear. Yeah? Hopefully it's clear. All right. So tomorrow's test will be offline mode, so you don't have to enroll in the Google Classroom. So there should be no Google Meet class tomorrow. Okay, so you can simply log into your Google Classroom and you can straight away download the questions and start the test at 9:30. Okay, so please have to submit your answers by 10:45. So just a kind reminder, a gentle reminder to you that I will not accept any submission after 10:45. Yeah, so if you submit the answers after 10:45, so sadly to say that your marks for test 1 will be 0. Okay, so you have to follow this schedule that we have set earlier. Yeah, right. Thank you very much for that response, yeah, on test 1. Right, so let us proceed with our lecture 8. Yeah, so lecture 8 will be a continuation from what we have learned from the last lecture 7. Yeah, so last lecture 7, if I can recall, I'm not sure why last lecture 7 you have a test this week apart from optical comm.
This is test on Sunday, doctor.
On Sunday. When Sunday? Is it this Sunday or next Sunday?
Yeah, the coming Sunday, the 6th.
I thought it's a semester break, right?
Yeah, but yeah, majority of them agreed to do on that day, so
Oh, okay. All right. So sorry to hear about that. Okay, never mind. Right. So let us proceed with lecture 8. Hopefully you can view the slide clearly. Okay. So lecture 8 will be covering topics of optical source, specifically on laser diode. So this is a continuation from light emitting diode that we have learned in lecture 7 last week. Yeah. Okay, I hope that you have good understanding, yeah, good fundamental understanding on on the light emitting diode, the LED, yeah, specifically on its principle of operation, yeah. So you have to understand well on that operation, especially on the spontaneous emission, yeah, how the laser diode can emit light, Yeah, so all of these fundamental things need to be understood clearly, and also on the issues related to uh, efficiency, yeah, efficiency of the LED. So these are the things that we have learned in lecture 7. Okay, and I did provide you the solution for lecture 7. Yeah, hopefully you can try to understand on the questions, on the question that have been posted in lecture 7 slides. Yeah. Okay, for this lecture 8, the topics is on laser diode. This will be the content of our lectures, yeah, in which we're going to have a look at these introduction to lasers. That's the first one. And then you're going to understand what is meant by stimulated emission. Okay, so in LED last time we learned about the spontaneous emission, right? So for the laser diode, the light operation is basically assisted, or I can say the basic principle of laser diode comes from this stimulated emission technique, yeah. And then you're going to see how laser diode is operated. Okay, so these are 3 important things to be covered in lecture 8, right? And this is from the CI. Okay, so our concern will be on this laser. So this is the things that we have learned in lecture 7, which is on the light emitting principle and also on the LED. So these have been covered in our lecture last week. So this week focus will be on lasers, yeah? Okay. So what is laser? So laser is actually an abbreviation from the words of these things, yeah, which is light amplification, L, A amplification, and then we have stimulated emission and radiation. So that is what meant by laser. So the word here is stimulated emission. Okay, stimulated emission. So that's really the word that is actually the fundamental of lasers, yeah. Okay, so the difference between LED and laser, as what we have learned in lecture 7, is on the production of light. Yeah, so we know that for the case of LED, the light produced is said to be incoherent. Yeah, incoherent. And I think I have informed or have taught in class what is coherency. So coherency is the case whereby the light is having same phase difference. Yeah, same phase difference, yeah, and also having same wavelength. So that's what we call coherency of light. So in case of LED last time, it produced incoherent light, but laser will produce coherent, yeah, coherent light. And this is mainly due to this stimulated emission, yeah. So if you can remember, in LED, the light produced by spontaneous emission, right? Spontaneous emission. That is why the light produced is said to be incoherent. But for the case of laser, due to this stimulated emission technique of light or photon generation, so the light produced is said to be coherent. Okay, so we're going to see after this how this stimulated emission method or technique in photon generation can produce coherent light. Yeah. Okay. The third thing about laser is that it's having narrow beamwidth. Okay, narrow beamwidth is something that is very important. It's very important because we want the light to be very focused in terms of intensity of light. Yeah, we need to have a very good intensity of light, as opposed to LED last time. It's not that good in terms of light intensity, because remember that the light, I mean the profile of light generation is based on, yeah, we have some sort like a cosinus cosinus profile of light. Remember last time we have learned this, yeah. So it's not focused, yeah, in terms of the beam generation or light generation. Okay, so these are the things that we can compare between the LED and also the laser, yeah. Right, and the thing is that in laser the light is amplified, yeah, the light is amplified, so that's why we're going to have high output power as compared to this LED. And this amplification is mainly due to this cavity resonance, yeah, cavity resonance in the lasers. So we're going to see after this what is meant by a cavity resonance, okay. And also one important things to be bear in mind for the case of laser is that it's having narrow line width or spectral width, yeah, in which the value of the spectral width is just a few wavelength, or few nanometer of wavelength, in which it is very good because it will reduce the dispersion. Okay, that's what we have learned in chapter 3, right? In chapter 3, we have learned about dispersion, in which dispersion is very much related to this line width or spectral width of the source. So if the spectral width is very high, so the results will be the dispersion will be very severe. Yeah. So that is why, as mentioned in class last time, for a long distance transmission of light, long distance transmission of light, we prefer to use laser because the dispersion effect will be very minimized. Why? Because of this very small or very narrow spectral width. So the effect of narrow spectral width or narrow line width is that the dispersion will be reduced, and as such, the light can be sent in a longer distance. Okay, so that is the important characteristics that we need to understand about laser as compared to the LED. Yeah, so for the LED that we have learned last week, the line width or spectral width of LED is quite large. Yeah, as compared to what we're going to learn in laser. Okay, so what we are having here, so these are the example, the figure of LED of the laser diode. It's very small. Yeah, it's very small, and it's also the figure or the laser diode that we can that we have in our lab also. Yeah, basically this kind of laser produce a red light. Yeah, a red light. Okay, this is what we call as HINI laser, helium neon laser. Yeah, the wavelength of emission for this laser is about 630 nanometer. Okay, right. So this is about lasers. So now we're going to see how the structures of lasers should look like. Right, so this is a graphical representation of lasers, the schematic structures of lasers, in which it is basically, because we know that laser is made of diode, okay, it's laser diode. So we're going to have also a PN junction, okay, as what we have seen in LED last week, is also composed of this PN junction, right? We have anode and cathode, connected to the power source, okay, to the voltage source outside. And we have also, okay, one more thing to be bear in mind is that the lasers is composed of two reflective mirrors, okay, two reflective mirrors. So the first one, the mirror is here. The first one is what we call as highly reflective, and then we have this side is made of partially reflective of mirror. Yeah, so partially reflective means that light will then emitted from this side. Yeah, emitted from this side. So that should be the side where the light will be emitted. Yeah, because basically these two mirrors will produce a cavity. Yeah, produce a cavity. So this part between these two mirrors is said is called a cavity. Yeah, resonance cavity. Yeah, resonance cavity. Okay, and this is the schematic, I mean the graphical figures of the lasers. Okay, so this is the laser. So this particular PN junction is just a small part in this laser. Okay, so we have a metal contact, which is the anode and cathode. So we have the PN material. Okay, and this is the resonance mirrors. Yeah, the mirrors, the cavity mirrors, and light will be produced from this side. Okay, so explanation is given here. Okay, so the laser is made of PN junction. Okay, PN junction, and it is formed by what we call as a laser material. So this is laser material. PN junction is made of laser material. So as what we have seen in LED lectures last week, this material must be a type of luminescence. Luminescence means that if we excite this material with a voltage source or current source, the light will be emitted. Yeah, light will be emitted. So this is what we call as a luminescent material. So for example, this material is indium gallium arsenide. Okay, we also have indium phosphide. Also, we can have gallium arsenide also. So these are the type of material that is said to be luminescence that can be used for both LED and also laser diode. Yeah. Okay. Then we have reflective surface or reflective mirrors at both ends. Okay, we have at one end is highly reflective, and another end is partially reflective, where the light is said to be emitted from this partially reflective mirror, and this will form what we call as resonant cavity. Yeah, resonant cavity. So the difference between the LED and laser diode, although it's made of same PN junction, same material, but the difference is on the formation of the cavity or resonance cavity. Yeah, in LED we don't have any resonant cavity, but in laser diode we have this resonant cavity, which will actually amplify the photon or the light in this cavity. So this we're going to learn this in the next slide. Yeah. Right, and then we have also the leads, the external lead that provide the connection to the outside source, the anode and cathode connections. Yeah, right. So this is the general structures of laser. So hopefully we can differentiate between the structures of diode, laser diode, and the structures of LED. So almost the same, but the difference is on the existence of these mirrors. Yeah, these two mirrors on both sides that produce the cavities. Right. So these are the processes that involve in the laser diode operation. So we call this as a lasing operation. Yeah? Lasing operation. There should be three processes involved. The first one is what we call as absorption, or sometimes we also call this as stimulated absorption. Okay, stimulated. Sorry, my handwriting is based on this tab. So hopefully you can. Okay, hopefully you can understand it. This is stimulated absorption. Also known as absorption only. Yeah. So this is the case whereby the atom in the ground state, okay, we have two states in laser, in energy band. So we have ground state. Yeah, we have a ground state and we have excited state. Okay, so for initial process, most of the atoms will be located at the ground state. Yeah, at the ground state. And this atom will absorb the photon which is emitted by other atom or externally injected photon. Okay, this is coming from the source, okay, from the outside source, and that's what we call this as stimulated absorption. Yeah, need to be stimulated. Yeah, the atom need to be stimulated. Yeah, so that it can then move, or can say that the atoms in the ground state will then absorb the photon. Yeah, and it will be then moved to this excited state. Okay, so it's given by this diagram down here. Okay, so we have absorption process here. So this is your initial position of the atom. So if we have external injected photon, yeah, this is given by the HV12. Basically, this is equal to the energy band value, which is Eg equals to E2 minus E1. The difference between the ground state and the excited state, and this equals to the HV that we have here. Yeah. So once we have this energy value, which is produced by external photon, so the atom at the ground state will be then excited to this what we call excited state. Yeah. So this is the excited state. E2 is the energy value, energy band value at the excited state. Yeah. Okay. So once it is I can say transited to the excited state, this atom, it cannot stay very long. Yeah, at most it can stay about nanoseconds value, about 100 nanoseconds value. So that is the typical time for the atoms to be localized. Yeah, to be located at this particular excited state. So the atoms at this excited state will be then emit a photon, emit a photon, in which it will then move to this ground state. Okay, so this is a process of spontaneous emission. Same things that we have learned in LED last week, spontaneous emission, in which the atoms at this excited state will then emit the photon of this value, in which this is the difference between the energy band value between E2 and E1. Okay, E2 minus E1 is equals to this energy band value, HV12. So the atoms at the excited state will move backward or move downward to this ground state. And as a result of this movement, the ground state, the photon will be emitted. Yeah, the photon will be emitted. So this is what we call as the spontaneous emission, which is same as what we have in the LED operation last week. Yeah. Right. So the things that is different between the laser diode and the LED is the third process, which is called as stimulated emission. So what is stimulated emission? So it is stated here that the atom in excited state will be stimulated to emit the photon by another incident photon. Okay, so as what we have learned previously, for the spontaneous emission, the atom is said to move down to this ground state naturally, naturally, without any force. But for the case of stimulated emission, the atom which is located at the ground state will be stimulated by another photon of light, and the stimulation of this photon will then incur the atom at this excited state to move down to this ground state. Okay, this is what we call as the stimulated emission. And the thing is that the photon which is produced by this effect is said to be in phase with the incident photon just now. Okay, so this photon that initially incident to this particular atom at the excited state, will be in phase with the photon that is generated by the stimulated emission. Okay, so that is what we call as a stimulated emission process. So in laser diode, there are three processes: absorption or stimulated absorption, okay, which is a movement from the ground state to the excited state. And then we have a spontaneous emission, a movement from the excited state to the ground state naturally. And stimulated emission is the movement from the excited state to the ground state by means of a stimulated photon. Yeah. Right. So this is the processes in laser diode. Yeah. Right. So in stimulated emission, so these are the things that we can say about the photon that is produced by stimulated emission. Okay. Number one is that the energy is identical. Yeah. E equals to HF based on this equation. The energy is identical means that the energy that is produced is identical between the photons that is excited and the photons that is produced by this particular stimulated emission. Okay, and the results will be on the identical wavelength. Okay, identical wavelength. That is why we're going to have a narrow line width for the case of stimulated emission. Yeah, when we have an identical wavelength, so the effect will be a very narrow line width that will produce. Okay, that should be the first effect of stimulated emission. The second case is that the photon will have identical direction, yeah, and as a result, we're going to have a narrow beam width. So as opposed to this spontaneous emission, okay, if you can base on this diagram, this photon emission will be, I can see the direction of the photon emission is said to be random. Yeah, it's said to be random. That is why it will produce a beam width which is quite wide, yeah, quite wide. So that should be the effect when the photon produced or photon generated is not identical in terms of its direction. Yeah, the direction of the photons in spontaneous emission is narrow. Okay. All right. So number 3 is that we're going to have identical phase. Yeah, identical phase in which it will result on this coherent wave, as what we have done last time. And the fourth one is that the polarization of the light is identical. Yeah, same polarization. So these are the things that we can say about the photons which are generated by the stimulated emission. So these are the 4 characteristics of the photons generated by the stimulated emissions. Yeah. Okay then. Okay. So basically there are 2 main processes. I mean 2 main things to be understood in the laser diode. principle. Yeah, the first one is a population inversion. Okay, what is population inversion? Okay, so basically in a normal condition, the atom, most of the atoms will be located at the ground state. Yeah, most of the atoms will be located at the ground state, in which the density of the atoms at the ground state is said to be higher as compared to the density of the atoms at the higher energy level, or the excited state. Yeah, this is in normal conditions. But for the lasing to take place, for lasing to take place, the photon need to be emitted. The photon need to be generated. The atom density at the higher energy level must be higher. Because if the atom density at higher level or excited level is higher, then only the photon can be produced. Then the photon can be produced, in which if the atoms is moved down, from the excited state to the ground state, then only the photon can be generated. So as such, we need to have a very high density of atom at higher energy level. Okay, so this process in which we want the atoms at higher energy level to be bigger in terms of its density as compared to the ground state is what we call as a population inversion. So this population inversion can be achieved by the absorption of photon, in which it is based on these injected, or I can say a stimulated absorption. Stimulated absorption, as what we have seen in the previous slide. So this inversion or population inversion can be achieved if we inject photon such that the atoms at the ground state can be then moved to the excited state. Okay, right. So this population inversion can be of 3 types energy level or 4 types energy level. Okay, depending on the systems. Okay, and basically there should be another metastable state, in which this metastable state will then permit the atoms to be localized in a longer time, in which it can be there for in a milliseconds duration, as compared to what we have learned before, when the atoms in this excited state, at most it can stay there for in nanoseconds time duration, and after that it will move down to the ground state. Okay, but in the case of this population inversion, the atoms will be excited to a new level, which is known to be a metastable state, in which the duration for the atoms to be there can be in millisecond duration, in which it will stabilize these lasers. Okay, so this is the population inversion process, in laser diode. Okay, and then we also have a optical feedback and laser oscillation. Okay, so this is basically happen in your laser cavity. Okay, so laser cavity is formed by placing reflectors at both ends. Is what we have learned in the early slides before, in which we have mirrors at both ends, highly reflective and partially reflective. Okay, right, and light will be first generated by this method of spontaneous emission. Okay, and the light or the photon which is generated by this spontaneous emission will be reflected. Will be reflected, and this is called as optical feedback. And this reflection will be back and forth in the cavity. So it means that it will be reflected by the mirror back and forth in the cavity, and this will then causing what we call as the stimulated emission. So initially, in laser production and laser process, we're going to have a spontaneous emission, but as a result of this cavity where light will be reflected back and forth in the cavity, then it will cause what we call as the stimulated emission effect. Okay, so the stimulated emission will create the avalanche multiplication. Okay, it will increase. It will increase from time to time. Okay, and after multiple passes, that gain can be large. Okay, means that after a few movement or few reflections back and forth, the net gain can be large, or net gain will be large, and as a result, the laser light will be produced. So the things to be known from here is that the onset of lasing is characterized by a specific injection current, which is known as a threshold current. Okay, this is given by this diagram, in which initially the light will be, the photon will be produced by this spontaneous emission. Okay, this is the region of spontaneous emission initially. So at this threshold value, threshold current, the stimulated emission will then start to produce, and this is where we call the lasing. Yeah, the lasing start to produce. Yeah. Okay, this is the place or the threshold of current where the lasing light or the laser light is start to produce. Yeah, so we can see the difference. This is the case of the spontaneous emission, and this is for the case of lasing or stimulated emission. So we can see it very much different in terms of the relative optical output power. Okay, all right. Okay, so this is a graphical figures to show you regarding the population inversion, the spontaneous emission, the stimulated emission. Yeah. Okay, so what we have here. All right. So this is your, sorry. Okay, this is your mirrors. Okay, this is two mirrors. Sorry, this is mirrors. Right, and this is your cavities composed of these atoms at the ground state. Yeah. So when we pump the energy, in which we do the stimulated absorption, yeah, we try to do the population inversion. Okay, the atom will be excited to the excited state. Okay, and I put here we have energy level 1, energy level 2. So the orange, the pink color here means that the atom is located at energy level 1. The blue color here showing that the atoms are located at the energy level 2. Okay, so this is the process of population inversion, in which the atom at the ground state is now excited to the higher level state, and this is the population inversion process. Yeah. Okay, so the atoms will be produce the photons by a spontaneous emission technique, yeah, which is the initial method of the photon generation. Okay, so that's why we have a spontaneous emission here by the green color. So the green color is the process whereby the photon is generated, yeah, by spontaneous emission. And somehow, due to this photon, which is said to be reflected back and forth by these mirrors, it will then produce a stimulated emission. Okay, and we can see that the stimulated emission is said to be started now. Okay, it's said to be started now, and as such, we can see that the lasing, the light is start to be produced. Yeah, so this is the laser light that start to be produced. So as the time increase, the stimulated emission is said to be built up. So again, you can see that from here, the magnitude of the laser light is said to be increased from time to time, and at the end, you're going to have full stimulated emission, and the laser beam will be generated. Okay, so this is the diagram which shows the basic laser operation. So hopefully you understand these laser operations clearly from this diagram. Yeah. Okay, so this is also a diagram that can be used to explain about the laser operation. Okay, so we have this is the lasers in terms of cavity. This is your mirrors. So we have a pump light here. Yeah, the pumping light, which is due to that will produce a stimulated absorption. And here we have the spontaneous emission. Okay, spontaneous emission produced when the atoms at the excited state move down to the ground state, and then it will produce the photon. But bear in mind that the photon produced are said to be randomly directed. Yeah, randomly directed. So we can see that how the direction of the photons looks like. Yeah, it's very random. Okay, this is the results of the spontaneous emission. So afterwards, we're going to see that the photons will be then reflected by the mirrors. Yeah, and the photons that is said to be reflected will then stimulate. Yes, stimulate another photon to be generated, which will be the stimulated emission process. And we can see that from this stimulated emission process, the photon direction is said to be directional. Yeah, it's said to be directional. And as such, the stimulated emission will be the major light production or the major photon generation in this cavity. And we can say that the lasing process took place completely, okay, and laser is said to be in full operation. Okay, so this is the process or the operations of the laser diode. Yeah. Okay, so in the cavity, this is what happens. Okay, so basically in the cavity there should be two light wave axes. Yeah, in which you're going to have one wave of light will move to the right and one wave of light will move to the left. Yeah. Okay, so we have this is your photon. So this is your mirror. That's your cavity. Okay, this is your mirrors here. Okay, so the light will produce will be then moved from the left and to the right. Yeah, it reflected to this mirror and move to the left. Yeah, and somehow it will move back to the right. So this is the case of the light wave that exists in your cavity. Okay, and we can say that from this mirror reflection, the total field in the cavity will be the sum of the moving light wave. Okay, so there will be a summation of the light wave. And there should be two cases that will exist. This first one is when a wave is said to have the same phase. So this light wave will act constructively. Yeah, and when the wave line are said to be out of phase, so that it should interfere destructively. So we're going to have two cases, constructive interference and also destructive interference. Okay, due to this similar phase or out of phase conditions of the light wave. And this will then lead to this standing wave pattern in your cavity, in resonance cavity. Okay, and we can say that if your cavity is having a length of L, yeah, these resonant frequencies of light wave that can exist inside the cavity can be written based on this equation. So F is the resonant frequencies in your cavities. Okay. M is your lasing modes. Okay, we have a lasing modes in your cavity. C is the speed of light. N is your index of the medium or index of the material or cavity medium. And L here is the length of the cavity. So based on this equation, we can say that in the lasers, in the cavity of lasers, they produce a lasing modes. Yeah, lasing modes. So it means that there are modes that is said to be produced in the laser. Okay, and is given by this equation in which we can obtain these lasing modes, a number of modes, if we know what is the frequencies of light in the cavity, if we know what is the refractive index of the medium, and also if we know what is the length of the cavity. So that will enable us to find out what should be the number of the modes inside your laser cavity. Okay, and from this equation, we can also write that there should be a frequency spacing between the adjacent cavity lasing modes. Okay, so we have, this is your lasing modes. Yeah, this is your lasing modes or longitudinal modes. So the frequency spacing between these modes is given by this equation. Yeah, delta F is equal to C over 2 over NL, in which we ignore the M. So the difference between these two modes is given by C over 2 NL. Okay, so that should be the frequency spacing between the adjacent lasing modes in your laser or emitted laser light. Yeah. Okay. So in terms of the wavelength spacing, we can also obtain it from the previous equation, in which we base on this equation that relates difference of the frequency and difference of the wavelength. Yeah. Right, in which by applying this equation, we can write that the delta lambda will be given by lambda naught squared over 2NL, in which delta lambda is the waveguide spacing between two lasing modes. Okay, so I put here that this is your lasing modes. Yeah, all of these are your lasing modes. Okay, this is your the profile of the lasers that will produce. Yeah, profile of lasers that can be produced. Okay, so this is what we call as a lasing modes, all right? And the different or the spacing between these lasing modes is your wavelength spacing. So remember, see that this is your profile of light depending on with regard to the wavelength. Yeah. So we have a wavelength spacing of delta lambda. Yeah. So this delta lambda will be calculated based on this equation where lambda known is the peak wavelength, right? And this delta lambda is what we have seen from the previous chapters, which is known to be your spectral line width. So you can calculate the spectral line width of the laser diode or laser source by simply based on this equation. Okay, so this is how we calculate the spectral line width of the laser. All right, hopefully you are clear regarding this wavelength spacing and also the frequency spacing. Yeah. Okay, so let's have a look at this example. So we are having this list of material, semiconductor material, and also the bandgap energy with regard to this material. The first question is determine the peak emission wavelength for laser diode fabricated from these materials. Okay, so for instance, if I base on this gallium arsenide, for example, okay, sorry, of silicon, for example, silicons lah, we take for silicons here. So silicons is having a bandgap energy of 1.12. So we need to find out what should be the wavelength emitted by this material. So as what we have seen in lecture 7 last week, the wavelength and the bandgap energy is interrelated by this equation, where the lambda is equals to 1.24 divided by the Eg, the bandgap energy. So from this equation, we can use it to calculate the lambda, the wavelength that we emitted by the material if we know the value of its bandgap energy. Okay, so if we have, for instance, silicon, so the lambda or the wavelength produced by silicon will be 1.24 divided by 1.12. Okay, so you can please calculate for me. By right, the answer for this will be equals to 1.1071 in the units of micrometer. Okay, so the lambda produced by this calculation is in micrometer unit. Okay, and then for instance, if we base on, let's say we go for indium phosphide, for example, indium phosphide. So the lambda produced by indium phosphide material will be 1.24 divided by 1.35, and this lambda produced will be equals to 0.9185 micrometer. So that should be the lambda that is said to be produced by this indium phosphide medium. Okay, so you can do the same things for the rest of this material. So bear in mind that you can calculate the lambda, the wavelength produced by this material or luminescent material, if you know the bandgap energy of it. Okay, number 2, the question here is we are having a gallium arsenide laser operating at this wavelength 850 nanometer with a laser length cavity of 500 micrometer. And given that the medium or the gallium arsenide medium is having a refractive index N of 3.7. So the question is, what are the frequency spacing and the wavelength spacing? Okay, so we need to obtain what is the frequency spacing and the wavelength spacing of this particular laser produced at 850 nanometer. Okay, so let's have a look at the solution for this example. So from the previous slide, we have seen that the delta F, which is the frequency spacing, be equal to C divided by 2 of NL. So C is the speed of light, which is 3 times 10 power of 8, whereas the N equals to 3.7, and the length of this cavity is 500 times 10 power of negative 6. So the answer for this will be equals to 81 gigahertz. So that should be your frequency spacing between the modes in your lasers. Okay, that should be the frequency spacing. Whereas for the wavelength spacing, we can base on the equations again from the previous slide. We're having delta lambda should be equals to lambda naught squared divided by 2 of NL. Okay, in which lambda naught is the peak wavelength emission, which is 850 nanometer. So that should be 850 nanometer squared and divided by the 2 N of 3.7 and the length of 500 micrometers. So the delta lambda, the wavelength spacing, should be equals to 0.95 nanometer wavelength spacing. Okay, so that's how we calculate the frequency spacing and also the wavelength spacing. So based on this, we can see that for this particular laser, the spectral width or the line width of this gallium arsenide laser is very small, which is about 0.195 nanometer only. So this is the value of your spectral width, of the gallium arsenide laser, based on the given questions here. Okay, hopefully you understand about this solution. Number 3, we are having a ruby laser which contains of a crystal of length 4 centimeter with the index of refraction of 1.78. Okay, and the peak emission wavelength is 0.55 micrometer. So the question is determine the number of modes, lasing modes, and their frequency separation. So basically it's very straightforward. It's just based on the given equation. Okay, so we know that this is a case of ruby laser. We are given the length of the cavity, which is 4 centimeter. We are given the index of the material, which is 1.78. We are given the lambda, the peak lambda, yeah, which is 0.55 micrometer. So based on these problems, we can say that from F equals to MC divided by 2NL, we can write that, from here, your M will be equals to 2NL F over C, and it can be written as 2NL divided by lambda. Okay, so we can obtain the M by this equation. M is your lasing modes amount, or lasing modes number in your lasers. So 2N, N is 1.78, yeah, 1.78, L is 0.04, and the lambda is 0.55 micrometer. So based on this, we can say the number of modes that we're going to have in your lasers is about 258,909 modes. So quite a huge number of modes in your lasers, yeah? Right, so that should be the number of modes, or I can say the number of lasing modes in your lasers, yeah? Okay, and I think for the frequency separation, you can try to solve this on your own, yeah, because it's similar to the above examples, just based on the equation of delta F equals to C over 2NL. C is known, N is known, and L is also known, so you can straight away find the delta F, which is the frequency spacing, and the answer for that will be 2 gigahertz. Okay, that should be the spacing for these lasers, yeah? Right, any question for this example so far?
So far, okay, Doctor.
Okay, you have a class after this or not?
Yes, Doctor.
Yes.
Oh, you have a class, yeah, all right. So I think I have to stop now lah, because we have few more slides to go. But since you have a class, so I don't want to disturb your next class. So we're going to stop the class here. Okay, so we're going to continue the lectures after the semester break, yeah, in 2 weeks' time, in which we're going to learn also about these laser light characteristics. Okay, so basically this will be the end of chapter 4. And after this, we're going to proceed further with chapter 5. Yeah, chapter 5 we'll be learning about the photodetector or photodiode. Yeah, so inshallah after the break, we're going to finish these laser lectures, and afterwards we're going to proceed with the chapter 5 on the photodetector. Okay, so with that, I thank you for attending the lectures. Before we end the class, I'm going to show you again the QR code for attendance. Yeah.
Thank you, Doctor.
Thank you very much. Yeah, thank you very much. Hope to see you again tomorrow morning for the test. Yeah.
Thank you, Doctor.
So, take care. Thank you very much.